Hey guys, welcome. So first and foremost, as always, thank you, Lord Christ, for everything. You are amazing. And second is, well, in this video we're going to discuss how to deal with surface area through revolution. In particular, I'm going to provide you two examples. Now, in previous video, we talked about volume through revolution, specifically the disc, washer, and cylindrical shells methods, right? Okay, cool. So this is somewhat like that in the sense that we're doing revolution still, but for surface area this time, yeah? Okay, cool. So the way you should start approaching problems on surface area through revolution is by distinguishing which of the formulas I'm about to write that you need, which of the formulas you ought to use, yeah? Okay, cool. So first thing first, your priority is, do I do 2 pi y ds, or do I do 2 pi x ds? So the first choice you have to make is, do I need this or do I need this? And the distinction is, well, this is if you are revolving about the x-axis. So x-axis is this, right? And if you're revolving about the y-axis, it's this. So the next question you should have is, what is ds? ds is the same as what we did in arc length. I have several videos on arc length, so check them out. But there in arc length videos, we said that ds is one of two things. It's either equal to the square root of 1 plus dy dx squared. All of this is in the square root, and then times dx, right? Or ds is the square root of, and it's going to be 1 plus dx dy squared dy. And so when do you use which? Well, you use this if your function is of the form y equals f of x, right? So in other words, your function is y in terms of x, and you use this if your function is x is equal to g of y. In other words, here your function is x equals stuff that has to do with y. As I said, I'm going to provide you two examples, so we're going to be able to use both this and this and this and this between the two examples, yeah? Okay, cool. But first thing first, let's talk about this little thing, and then we will get to the two examples I just mentioned. And this little thing will like complete your understanding of surface area through revolution. Now, if I talked about the surface area of a cylinder, right? Okay, surface area of a cylinder. Let's say the cylinder looks like this. That's good enough, right? We'll live. Okay. So if I talked about surface area of a cylinder, what would that be? Well, that would be this, which is the lateral area. The lateral area would be like if you cut the cylinder with a scissor, I suppose, and then you flatten it out. The lateral area, which is the surface area of the curved part, is going to be, well, when you cut a cylinder open and flatten it out, it's going to turn into a rectangle, and the width of the rectangle would be like the circumference of either the top end cap or the bottom end cap. And so if the cylinder has radius r, then this would be 2 pi r, right? That's the circumference. This here would be like the length around once it's flattened out. And then, of course, the height h. And so the lateral area of a cylinder is 2 pi r times h, because, well, it's the area of this rectangle, right? Okay, but then for the surface area of a cylinder, you also have to add the top and bottom end caps, right? The areas of this circle, and they're identical circles if it's a cylinder. So we need to add to this 2 pi r squared. because pi r squared would be the area of this top end cap, but the bottom end cap has the same area, and therefore 2 pi r squared. Now, I mentioned this to say that when we're doing surface area through revolution, so when we're doing these problems, we're only covering the lateral area. Remember, when we're doing solids of revolution for volume, well, the cylinder would be filled in, so we're finding, like, you know, how much it could contain, right? Like, that's what volume is, right? Okay, but when we're doing surface area through revolution, we're only talking about the lateral area of whatever shape we're talking about. Whatever shape we're working with, we're talking about the lateral area. We're not talking about the bottom end cap and the top end cap. These are not added in the calculation of surface area through revolution. So I just said that the lateral area of a cylinder is 2 pi RH. So if we did it using these formulas, well, all I'd have to do is basically like anchor this cylinder in the XY plane. So I'm going to, so this is a line through the cylinder. So it looks like I missed, this thing's sticky. Okay, so it would be like this. Oh, Jesus Christ, my bad, guys. So this is the y-axis, right? And let's say that the x-axis is like right here. Right? Okay, so the x-axis is right here. Got it. So the x-axis. Okay, well, notice that now what we're revolving is the vertical line. Sorry, maybe I should have kept the ruler. So if this is the vertical line, x equals r, well, that is what we're revolving about the y-axis. First of all, we're revolving about the y-axis, I just said, right? Second of all, what we're revolving about the y-axis is this line x equals r. Got it. So if we're doing the cylinder's lateral area, that is its surface area on the curvy part, using this calculus, then first of all, from what I just said, from everything I'd said so far, we know that we're revolving about the y-axis, so we need this formula. So we're gonna go, all right, so that's 2 pi, right, left. Okay, so we're gonna go 2 pi x and then ds, right? Okay, and let's say along the y we're going from 0, and let's say that this is h, because we said that the cylinder's height is h, and so then from y equals 0 to y equals h is our limits, so 0 to h. And I know that our function is x equals r. It's a constant function. Well, yes, here, since I haven't decided what r we're using, r is kind of a variable, but it's not. It's a constant. It's a fixed distance, right, from the y-axis at all places. So it's x equals r, whatever r may be. But r is a constant, some constant, right? Okay, but the point is that we have x equals, and so we're using this ds. So this ds is going to have at the end of it a dy, because we're using this one. And so it makes sense that I'm integrating along the y-axis, right? Okay, but if x is equal to r, what's ds? Well, ds is going to be equal to the square root of 1 plus dx dy squared. But if x is r, dx dy is going to be equal to 0, because r is a constant. So we have square root of 1 plus dx dy squared is that. And of course, at the end of ds here, we need to have dy again, because our function is x equals. So ds is simply the square root of 1, which is 1, dy, so it's just dy. ds is just dy in this specific case. So I change this ds into dy. Got it. Now, this x here, it's r, because we said x is equal to r. So we have next that this is equal to 0 to h, and then 2 pi r dy. Fine, 2 pi and r are all constants, so we could write them in front of the integral. So we have 2 pi r, 0 to h, and then dy. But the integral of dy is just y, so we have 2 pi r y evaluated from 0 to h. We plug in h first, so we get 2 pi r h, and then we plug in 0. Well, we get 0 when we plug in 0, so we have this minus 0. I won't bother writing it, but it concurs. It agrees with what we said was the lateral surface area of a cylinder, yeah? Okay, cool. So I just wanted to make abundantly clear that this surface area through revolutions does not cover any end caps you may have in your shape. Okay, but now that we have done this, let's get to the two examples that I have in my dome. Okay, so at the top of my dome, freestyler, no, okay. So, now what? Well, let's do the, one about the, x-axis, right? So, this is going to be, considering the function y equals the square root of, and it's, 9 minus x squared, and then, we're doing this from -2 is less or equal to x is less or equal to 2, and we're revolving about the x-axis, right? Okay, x-axis. Okay, got it. All right, so, well, notice that y equals the square root of 9 minus x squared. That's a circle with radius 3 centered at the origin. Well, it's the top half of a circle. I can convince you this way. Square both sides. That says y squared is equal to 9 minus x squared. And then I could write this as x squared plus y squared is equal to 9. And so this is clearly a circle centered at 0, 0 with radius 3. Yeah? Okay, cool. Now I have videos on the equation of a circle, the derivation, as well as examples, so watch that if you need to learn more about circles. But for now, 1 second. The story of my life. Come on, man. What are these doing? I'm making a video, math video. Okay. Why are they trying to save lives and stuff? Okay. So I'm saying let's quickly graph this to get our visual. You don't need to have the visual in order for you to succeed in these problems, but you know, for this one, we can do it quickly. So let's just do it. And there's more than one reason I want to do it, but you know, visualizing what you're doing is always helpful. So like, okay, from what I said, the positive square root when you isolate y from this equation is going to be the top half of the circle. The negative square root when you isolate y in this equation is going to be the bottom half of the circle. And we have the positive square root, so that's the top half of the circle. So we've got something that looks like this, right? So what I just drew is this guy, so long as this is -3, this is 3, and that's 3. Now we're not finding the surface area that we get when we revolve this about the x-axis. We're doing it from -2 to 2, so our surface area, that's, well, that shouldn't be where -2 is. -2 is more like here, right? So let's say this is -2, and then like 2 is like here, right? Then when we revolve this, what are we gonna get? Well, we're gonna get something that looks like the, okay, fine, it's like overlapped on the, okay. Well, you get it. Okay, so it will look like this. My drawing here is less than convincing, but you get it. Basically, like, I'm saying that, like, it's not gonna be a sphere, right? Because if we take the entire semicircle and revolve it about the x-axis, it's gonna be a sphere. But we don't have a sphere. It's like a sphere where we like took a knife and chopped off even ends on either side. But the reason why I care to make the drawing is to say that, like, well, the surface area we're finding is about this curvy front part and the back part. We're not doing the end caps, as I already explained in this cylinder. Okay, and this visual is ugly, so let me get rid of this. Like I said, visual not required. Okay. For succeeding in these problems. So the most important thing is we pay attention here, and it says x-axis, so we know that we must use that formula. And I'm done convincing you that this is a circle, so we could get rid of that. So we start with this formula. So we go, all right, so what we've got is integral, and then I could write the 2 pi right here, right? So 2 pi, and then y ds. Got it. Most of the work is going to be spent on figuring out what ds is, and since our function here is of the form y equals, we know that ds is going to be this guy, right? The top guy, right? Okay, because it's y equals f of x, right? Okay, and at the end of it is dx, so good thing that the limits of integration are about x. We can throw them on right now, so -2 to 2, right? Okay, as I said, we need to occupy ourselves most of the time when we're doing this on just figuring out what ds is. ds is the square root of 1 plus dy dx squared. So if y is this, well, notice that y could be rewritten as 9 minus x squared to the positive 1/2. Then dy dx is going to be equal to, it's going to be 1/2 9 minus x squared to the negative 1/2, and by chain rule times negative 2x, right? Okay, got this. So this simplifies to negative 2x over 2 times the square root of 9 minus x squared, right? Okay, and then this 2 and this 2 we could get rid of, and then we have to do dy dx squared, so we square this, meaning we square this, and when we do, what we're going to get is x squared over, and then it's going to be 9 minus x squared. Got it. So in here I plug in x squared over 9 minus x squared. Okay, pause for a second. Another ambulance. Have resigned. Saving lives has never been this unappealing to me, but anyway, let's continue. Okay, so we have ds here at the end of it, like we said, has a dx, and so far this is the progress we've made on ds. Notice that, like, well, to simplify inside the square root, I could write 1 as 9 minus x squared, and then over 9 minus x squared, meaning I can extend this division sign, right? I got common denominators inside the square root. That's all I'm saying. Don't forget that there's a dx right here, right? Okay, cool. And now notice that we have 9 minus x squared plus x squared. So minus x squared plus x squared get rid of each other. And so we just have a 9 here. And I wish I could just slide this to the left, but I can't. So I have to rewrite it. There we go. Okay, and then we can simplify this further as saying ds is equal to the square root of 9, which is 3, over the square root of the denominator, which is square root of 9 minus x squared. You'll see that this will work out really nicely. Got it. Okay, so we come back and be like, I don't need this, and so now we need to put ds right there. So we've got now 2 pi, right, and then integral from negative 2 to 2, and then y, and then ds, right? Y, and then ds is 3 over square root of 9 minus x squared, and then dx at the very end, right? Okay, cool. Now we're integrating with respect to x. The dx lets us know that, and also our limits, right? So this y, we have to do something about that y, right? But lucky for us, y is in terms of x, and so we're good. All we have to do is, in place of this y, right, what y is, which is square root of square root of 9 minus x squared. And how convenient, because this is over 1, and so we see what we could do is boom, boom, these cancel. That worked out really nicely, and this 3 we can lump together with the 2 pi, so we're going to get 6 pi, and then it's going to be integral from negative 2 to 2 of dx. Fine, that's just 6 pi x evaluated from negative 2 to 2. When we plug in 2, we get 6 pi times 2, so that's 12 pi, and then a minus, when we plug in negative 2, we're going to get negative 12 pi, so together these make 24 pi. Yeah? Okay, cool. So there we are. So we're done. We see that the surface area of this here, when we revolve it about the x-axis and consider negative 2 to 2, the lateral part that I drew, that has surface area 24 pi, yeah? Okay, cool. So we just did one about the x-axis where we used this version of ds, and so let's do an example where we do about the y-axis, although I did do that in a very basic example of the cylinder, right? Cylinder lateral area at the start, but yeah, let's do one example about this guy, and then we could say like we're done, right? Okay, cool. So here goes. So this is the example. Again, from the top of my dome, freestyle. No, okay. So we go. Okay, sorry. Okay, all right. So what is that? Well, we go. The function is x equals root y, and we're considering 0 is less or equal to y is less or equal to 1, and this is about the y-axis. Okay, so immediately we see it's about the y-axis, so we've got to write that. So we got to be like, okay, so 2 pi, again, the 2 pi could be written in front of the integral, otherwise x ds. Okay, and we have x equals stuff that has to do with y, and so we know that ds has got to be this, but I already foreshadowed, actually literally told you that. Okay, so ds is going to equal square root of what? It's going to be square root of 1 plus, sorry guys, 1 plus dx dy squared. So if x is equal to root y, that means x is equal to y to the 1/2. dx dy is going to equal 1/2 y to the negative 1/2, right? Okay, so that's going to be 1 over 2 root y, right? Okay, cool. So this is dx dy, but in ds we have dx dy squared added to 1, so we should square this. So short. Okay. Okay, so and then so that means we square this, so this is going to be 1 over 4y, right? Okay, got it. And so we've got 1 over 4y right here. Now, just as before, we want to simplify inside of the square root, and also let's not forget that at the end of this we have dy, right? And so good thing our limits are about y, and let's throw them on, actually 0 to 1, right? Okay, but yeah, let's simplify inside the square root. So we've got ds is equal to the square root of what? The square root of 4y plus 1 over 4y, right? And then of course dy at the end of this. Got it. Now using square root rules, we could write this as the square root of, you'll see why we'd want to do this, but 4y plus 1 over the square root of 4y in the denominator, but that's 2 root y. Okay, got it. And then of course dy at the end. Okay, cool. So we've got the replacement for ds. So let's put that in place of this ds. So that means we've got, so far we've got 2 pi integral from 0 to 1, and then it's x. ds is at the far right, so that's root 4y plus 1 over 2 root y, and then dy, right? Got it. But x, remember, is root y, so we replace x with root y, right? And then we see that this happens, right? And this 2 here we could throw as a denominator to the 2 pi right there, so we get rid of this, we get rid of this, get rid of this, get rid of this. Okay, so, and get rid of this, so we just have pi times integral from, let me write that pi bigger, it's got all the space it needs now, pi times integral, and then root, it was 4y plus 1 dy. Okay, you really don't need to do use substitution here, but you can if you want. For some of you it's probably helpful, and so